This lecture we are going to do dispersion. Okay, dispersion is as such a general concept. It is not related only with the light. Okay, but here we are going to study only the things that is specific to light only. Okay. Now, if I want to define dispersion, how will I define it? How would you define this dispersion? In the most general way, we can define it as dispersion is separation, or we also call it as splitting of a light containing more than one wavelength into its components. Okay. Okay. For example, splitting of white light into its component colors. Okay. Component colors. Okay, this is a very famous acronym, WIGOR. Okay, it represents all the colors which are present in white light. Okay, so white light is a mixture of different wavelengths. Okay, each color has different wavelengths. So we have the 7 distinct wavelengths in white light. So this is for violet, indigo, blue, green, yellow, orange, and red. Okay, so this is splitting. When all the wavelengths are together, all the colors are together, it makes white color. Now, the process of separating it into its different components is known as dispersion. Okay. Now, why it happens? Okay. It happens because different wavelengths have different refractive index in the same medium. Okay, now dependence of refractive index of a medium on wavelength is given by Cauchy's law. Now, what is this Cauchy's law? It says that refractive index of a given wavelength. Okay, suppose so this first of all, this itself is a very interesting concept. Okay, so for example, water. Refractive index of water is 4 by 3. Now, what this concept is saying is that for the same medium, for water, different wavelengths are going to have different refractive index. So it is 4 by 3. It is 4 by 3 not for every color. For red, it is going to have different refractive index. For violet, for green, for yellow, for different color, the same medium is going to have different wavelength. And that is the basic foundation behind this process, which is dispersion. Okay. Now, how the refractive index mu depends on wavelength. It is given by this Cauchy's law. It is equal to A plus B over lambda square. Okay, it is of this form. Okay, A and B are positive constants, okay, for given medium, okay, okay, that's fine. Let's accept this, that refractive index depends on wavelength. That's fine, accept it. How it results into dispersion? Let's try to understand that. How this thing results into dispersion. Okay. Let's do it step by step. Sequentially we are doing it. That will help us understand it. Okay. Let's say that I have a light. This is my light. This is a slab. Some medium. Okay, not slab. Let's say that I have some medium here. This is air. And I have some medium here. Its refractive index is mu1. Let's say it is mu1. And some light is incident. Okay. Forget about dispersion. Okay. Dispersion happens when I have a mixture of wavelength. This is a single wavelength. I have a light ray, let's say a red color light. So red color is going to have single wavelength. So let's say this is red color light. It is incident on this interface, air and medium, and this is angle of incidence. Let's say it is I. So it is entering a denser medium. It is going to bend towards normal. Let's say that it bends like this, and this is the deviation. This is delta 1. This is deviation. Okay. Now I have same wavelength, same light, exactly same light. This is lambda, and this is angle of incidence is I. This is air, and this is some other medium. Its refractive index is mu2. Let's say that mu2 is more than mu1. Try to understand this. Mu2 is more than mu1. Okay. Now, here also I am going to have some deviation. Now, I am going to have this deviation delta 2. If I ask you, what is the relation between delta 1 and delta 2? Between delta 1 and delta 2. First, both are equal. Second, delta 1 is less than delta 2. And third, delta 1 is more than delta 2. What do you think? Can you figure out? Can you find out from whatever you already know, using no other new concept? You can do it if you think a little bit. Okay. Angle of incidence is same, both. Lambda is same lambda. But now here the medium is different. This is medium mu1, this is medium mu2. If medium is different, then angle of refraction is going to be different. Let's say that it is R1 here, R1, and this angle is R2. Okay. Now sin I, 1 times sin I is going to be equal to mu1 sin R1. It is going to be equal to mu2 sin R2. Both are going to be same. Now, if mu2 is more than mu1, so this product is going to be same, mu1 sin R1, mu2 sin R2. Now, if mu increases, if this mu2 is more, okay, and the product has to be constant, in that case, sin R2, it should be less than sin R1. Okay, that means R2 should be less than R1. Okay. Now, what about delta 1? Here that means this is my original light. Okay, this is the original path here. At this point, the deviation happens. Okay. Now this is This is R1. So when mu increases, then angle of refraction decreases. Okay, so this light will further bend. Okay, so what is effect on delta 2? Delta 2 is going to be more than delta 1. Okay, delta 2 is going to be more than delta 1. Okay, you understand this? It's pretty simple, obvious, almost obvious. Okay, that means delta 2 is going to be more than delta 1. Okay, that means if mu increases, okay, then this also increases. Okay, makes sense. Now you can create one connection here. Refractive index of a medium is related with its bending power. More the refractive index, more the bending. Okay, this is bending. This deviation is nothing but bending of light. More deviation means more bending. More refractive index is more bending. Okay, so more higher the refractive index, higher will be bending. So refractive index is related with bending. Okay, understand this? Now, so let's note down this point separately. It is going to help us. Okay, it is going to help us. Okay, what is the concept here? Mu increases, delta increases. All right. Now, one other case. Let's say I have this medium air, and this is a medium. Okay, some medium I do not know. Okay, some medium. Now, in this medium, a light is incident. But now this light is not monochromatic. That means it is not single wavelength, but it is a combination of wavelength, lambda 1 plus lambda 2, both. Lambda 1, lambda 2. I have two wavelengths together, traveling together. Okay, they hit this interface. Now, according to this Cauchy's law, if lambda increases, then mu decreases. If lambda increases, then mu decreases. Okay, so I can combine this with Cauchy's law. What is Cauchy's law? Okay, lambda increases, okay, mu decreases, then bending also decreases. I am combining this with this result here. Okay, so if lambda decreases, okay, mu increases and bending also increases. Do you see this? Now, let's say that I have these two wavelengths, lambda 1 and lambda 2, which is more than lambda 1. At this point they hit. Now, this medium is going to have different refractive index. The same medium is going to have different refractive index for these two wavelengths. Okay. The refractive index for which wavelength will be more? If lambda 2 is more than lambda 1, when lambda increases, mu decreases. Okay, that means mu 2 is going to be less than mu 1. That means deviation in this light ray, okay, delta 2 is going to be less than delta 1. What do you think? This is the original path for both wavelengths. The moment they enter this medium, they are separated. Now there is going to be different deviation in both. Okay, lambda 2 is less than lambda 1. That means this is going to be lambda 2 and this is going to be lambda 1. Delta 1, okay, deviation is delta. This is not lambda, it is delta. This delta. This is known as dispersion. This is known as dispersion. Okay, that's the same thing that we are discussing, that we discussed here. So this is a mixture of light. It breaks. The moment it enters this medium, it breaks. This is dispersion. Okay, understood? Now, what will happen with a white light? Okay, white light. White light. Okay, let's say that some light is incident here. It is white light. This is white light. Okay. Now the moment it enters this medium, okay, this is air, and this is some medium. Okay. Any medium. It can be water. It can be glass. Any medium. Okay. Any medium. Okay. This is true for all the mediums. Okay. Now, so this white light is made up of 7 different colors. 7 different colors is 7 different frequencies, 7 different wavelength. Okay, so now they are going to have different refractive index. What will be relation between the refractive index of these seven colors? Okay, we can find out if I look at the spectrum. If I look at the spectrum, this is violet, this is indigo, blue, green, yellow, orange and red. Orange and red. Okay, this is red. What is the relation between their wavelengths when I go from violet to red? Okay, when I go from violet towards red, then lambda increases. This is something that you have to remember. The wavelength of in this spectrum of visible light, wavelength of red is maximum and wavelength of violet is minimum. So when I go from violet to red, lambda increases. When lambda increases, refractive index decreases. Okay, and then this deviation also decreases. More refractive index, more deviation. Okay, that means lambda of R is more than lambda of violet. Okay, this results into refractive index of R being less than refractive index of violet. Okay, and refractive and deviation in R is going to be less than deviation in violet. So different colors are going to have different deviations. Okay, in general, okay, refractive index corresponding to yellow color. In general, refractive index corresponding to yellow color is average of red plus violet. In general, this is in general. Okay, I am not talking about wavelength. Wavelength is here. This is yellow here. It is not in between. We are talking about this refractive index. In general, refractive index will be approximately average of these two. General. Okay. Otherwise, in some problem, if this refractive index is given, then we will use that value. Okay, you will encounter some problems where the refractive index of only R and V are given. Refractive index of yellow is not given. Okay, in those problems we will apply this relation. It will be average of these two approximately. Okay, this is about the relation between their wavelength and refractive indices and the deviation. So the moment it enters, it is going to break into 7 different parts. Okay, which one will have this deviation? Red will have minimum deviation, and violet is going to have maximum. Okay, the moment it enters, it is going to split like this. This is a red color, delta R. It is going to have minimum deviation. Okay, and this is going to have maximum deviation. Okay, this is delta V. Okay, delta R and delta V. Okay, yellow is going to be in between. Yellow, violet and Okay, this is a delta in A. Okay, this is known as dispersion. Now this single light ray is now dispersed, it is now diverging, it is now spreading. Now what is the angle of spread? Angle of spread, this is the angle between these two lines, these two extremes. Okay, think about it. This is the angle of spread, the angle in which this beam is spreading. Okay, this is known as, okay, I'm going to clean all this. Okay, we are defining few terms related with dispersion. Note it down, I'm going to clean. Okay, angular dispersion. Theta is equal to deviation in violet minus deviation in red. What is this? We are defining new terms to study this process. Okay, dispersion. So this angular dispersion, the angular spread in which all the rays are present. So this whole thing is known as angular dispersion. Okay, the name itself suggests angular. This is the angular dispersion here. So it will be equal to this whole angle delta V minus this delta V delta R. Okay. Now mean deviation. Okay. What is mean deviation? Mean deviation is equal to delta Y. Different colors are going to have different deviations. Red is going to have minimum deviation, violet is going to have maximum deviation. Different colors are going to be between these two extremes. They have different deviations. Okay. So if you talk about the average, what is the average deviation? Okay. So this yellow is approximately in between. So the deviation in the yellow color is known as average deviation or mean deviation. Mean or average, both are same. Okay, and now we define a new property that is known as dispersive power. Okay, dispersive power is equal to angular dispersion over mean deviation. Okay, omega is equal to theta over delta y is equal to delta V minus delta R over delta y. This is known as dispersive power. Then how to find it? How to find this deviation? For a given medium, what will be its dispersive power? Okay, that we can easily find out. Okay, if we make use of a thin prism. Okay, let's see. Okay, thin prism. Okay, angle A. What is deviation from a thin prism? Last lecture we studied this. It is going to be equal to mu minus 1 into A. Now, if I take a thin prism, you see, I am drawing a big picture here, just for clarity. Understand this. This is a big picture. It is just for clarity. Otherwise, it is a thin prism. Okay, so I am going to make use of this relation. This angle is very small. I am drawing it big just for the sake of clarity. Okay, you understand that. Now, let's say that I have this light. It's a white light. Now, the moment it enters, it breaks. This is the original direction. The moment it enters, it breaks into its components. The moment it enters, it breaks into the components, okay? It's like this. And then finally, this also is going to deviate. What color is this? Minimum deviation in red, maximum in violet. Okay, that means this is red color here, red color, and this is violet color here. This is my red color here, and this is violet color here. And if I keep a screen here, I am going to get all the colors here, like in rainbow, Okay, do you see this? Do you understand? Okay. What are the deviations? This is delta R, okay, and this deviation here is delta V. Now, yellow will be somewhere in between here. This is my yellow color. This is red, this is yellow, and this is violet. Okay, yellow here. Now, yellow is going to have some deviation like this. This is going to be my deviation in yellow color. Now, if angle is small, okay, what is going to be delta R? Delta is equal to mu minus 1 times A. Okay, what is delta R? Is going to be equal to mu R minus 1 times A. Okay, similarly, what is delta V? It is mu V minus 1 times A. Okay, and what will be delta Y? This becomes mu Y minus 1 times A. Okay, makes sense? What will be angular dispersion? Angular dispersion theta, okay, is going to be equal to this delta V minus delta R. Okay, it is going to be equal to mu V minus mu R times A. Okay, and what will be delta Y? It is already given, mu Y minus 1 into A. What will be dispersive power? Omega is going to be mu V minus mu R over mu Y minus 1. A does not appear here. What appear are refractive indices of different colors, and that will be a property of medium. Okay, so is a property of medium. Note this down. Dispersive power is a property of medium. It is a positive constant. Dispersive power is a property of medium. It is a positive constant. Understood? Let's solve some problems. Okay. What will be unit? It has no unit. It is just a ratio. What is unit of this? This will be in angles. This is angle, but this has no unit. Dispersive power, no unit. Property of medium. Okay? Positive constant. This is positive, this is positive. Positive constant. Okay? So that's it. Note on everything clearly in your notebook. All the formulas at one place. Now we are going to do problems. Okay? Simple problems are asked. Very simple problems are asked. Okay, calculate angular dispersion. Okay, average deviation. And dispersive power. For a prism of angle 4 degree. Okay, for a prism of angle 4 degree, having mu r is equal to 1.62, mu yellow is 1.63, and mu violet is 1.64. Okay, find it. Okay, next. What is net dispersion and deviation? Net dispersion and deviation. Okay, it's like this. This is a 4 degree. This is a 3 degree. This is the first case here. This is a crown prism. This is a flint prism. Crown and flint. Okay. And second, this is 4 degree. This is 3 degree. This is crown and this is flint. Okay. For crown, okay, mu r. And for flint, mu r. This is let's say 1.67, and mu v. Okay, mu r and mu v, they are going to be, okay, this is going to be higher. So this is 1.6 and this is 1.67. Okay, 6, 7 and 6. And then let's say it is 1.4 and mu v is 1.6. Not 6, but it is 6. Only 7, 6 and 7, that's it. What is crown and flint? Type of glass. Okay, just it's kind of a brand. So I have two brands. I have hundreds of types of glasses, hundreds of types of brands, hundreds of brands of glasses. Okay, so these two prisms are made of two different brands of types of glass. One glass is known as crown glass, and the other glass is known as flint glass. So both glasses are going to have different refractive indices, and they are given. In each case, I have to find what is net dispersion and what is deviation, net deviation and net. When we say net, that means the net average deviation. When I say dispersion, net angular dispersion. Okay, understood? Let's see how we can solve it. And okay, let me write one more problem. A prism of angle 4 degree and refractive index 1.7. Okay, a prism of angle 4 degree and refractive index 1.7 is combined with another prism of angle, let's say angle A, and refractive index 1.5. Okay, find A. Okay, I have to find A to produce. Okay, find A to produce dispersion without deviation. Dispersion without deviation. Now this is a little confusing problem. Little confusing. Refractive index is given. So for which wavelength, for which color, it is not specified. Then we will have to assume something by default. Okay, we will see what we have to assume. Let's try this. Okay, delta is equal to mu minus 1 times A. Note down the problems and solve it. Let's see if you are getting the same answer. Okay, understood? You have to stop now, solve it, then we are going to discuss it now. Okay, angular dispersion, deviations in different colors. Red is equal to 1.62 minus 1 times 4 degree. This is 0.62 times 4, this is 8, and 4 and 6 is 24, so 2.48 degree. Okay, in yellow color it is 1.63 minus 1 times 4, 0.63 times 4, so this is 2.52 degrees. Okay, makes sense? Does that make sense? Okay, now deviation in violet color, 1.64 minus 1 times 4, 0.64 times 4, 2.56 degrees. Okay, now angular dispersion. Angular dispersion, okay, theta is equal to delta V minus delta Y, delta R. Angular dispersion, the angle in which all the rays are present, the angular spread. Okay, so 2.56 minus 2.48, 0.08 degree, 0.08. Okay, average deviation is also known as mean deviation. Mean deviation, delta Y is equal to 2.52 degree. That's it. Okay, that's it. And then dispersive power, omega. Dispersive power, omega, is simply theta over delta Y. That's it. This is my answer. Okay, this is my answer. This is going to be 0.08 over 2.52, so 8 over 252, and then you simplify this, we have the answer. This will be dispersive power of this medium having these refractive indices. Okay, you understand this? You see, angular dispersion, mean deviation, all of these will depend on my prism. But this value, dispersive power, it is property of this medium, this material of which the prism is made. Now, in the second case, we did this problem, not this problem, but the similar problem in the last class. In this case, the deviation is going to be added, okay, and here it is going to be subtracted. It's like this, okay. Now, net dispersion and net deviation. First, let's find the net deviation in all the colors. Net deviation in all the colors, we find it. Here, ground glass. What will be mu y for yellow? Red and violet is given. Yellow is not given. In the last problem, yellow was given. It was specified. Here it is not given. It will be equal to average of these two. 1.6 plus 1.7 over 2. This becomes 1.65. Okay, do you see? And here, this is going to be equal to mu y for flint glass. Average of these two is 1.5. Average. Okay. Now, first case, when I have prisms arranged like this. Okay. Let's say that this produces delta 1, this produces delta 2. Delta 1, delta 2. Then what will be net? Delta is delta 1 plus delta 2. In this case, in the other case it is going to be subtracted. Okay, so net delta in red is equal to 1.6 minus 1 times 4 degree plus here 1.4 plus 1.4 minus 1 times 3. Okay, think about it. This is going to be equal to 0.6 and 4, so 2.4 plus 1.2, this is 3.6 degree. Okay, 3.6 degree. Okay, delta yellow is 1. For the crown one, it is equal to 1.65 minus 1 times 4 plus here it is 1.5 minus 1 times 3. This is going to be equal to, this will become 2.6 plus this will become 1.5, this becomes 4.1 degrees. Okay, that's how we calculate. And then delta y dot, the net deviation, is going to be this 1.7 minus 1 times 4 plus here 1.6 minus 1 times 3. So 2.8 plus 1.8 is 5.6 degree. That's it. Net dispersion is equal to delta V minus delta R. So 5.6 minus 3.6, it is 2 degree. Okay, it is 2 degree. And then net deviation, that means net average deviation, that means net deviation in delta y, it is equal to delta y is equal to 4.1 degree. Okay, what is omega? Is 2 over 4.1, approximately 0.5. This is the dispersive power of this combination. Okay, this is net dispersion, net deviation. Okay, then in the second case, we just have to subtract it. In the second case, if it is like this, here, it is going to be minus. So I am going to write minus here. Minus here, okay? So this is 1.2 degree. Here also I am going to write minus. Everywhere I am going to write minus here. Okay. This is going to be equal to 1.1 degree. And this also is going to be equal to 1. Okay, that's how we do it. This is net. Okay, it is equal to mod of this, so 1 minus 1.2, it is 0.2. Okay, we will see what will happen. This will be 1.1. Okay, so this is a dispersive power. What is the difference between this case and this case here? The sequence of colors will be reversed. In this particular case, deviation in red is now more than violet. Here it was less than violet. Okay, this deviation here is more. So the sequence of colors, the final spectrum is going to be reversed. Okay, now by adjusting, okay, let's do this one here. The next one, a little confusing one. What is the meaning of dispersion without deviation? What deviation? Deviation in what color? Yellow color. When refractive index is given and nothing else is specified, we know that refractive index depends on color. Different colors are going to have different refractive index. Okay, so if I am saying that my refractive index is 1.7, it is for what color? It is for what color? It is for yellow. Here also, yellow is 1.5. That means I want deviation, I want dispersion, but I don't want deviation. I do not want deviation. That means I do not want deviation in yellow color. It is not possible that all the colors will have no deviation. Think about it. Dispersion is going to happen. I have some combination. This is my combination. By adjusting the values, this is A1, this is A2. Okay, this is mu1 and this is mu2. By adjusting these values, okay, I can find different results. I can adjust them such that delta y becomes 0. Delta y becomes 0. You can adjust that. Okay. Here we are adjusting. So that will be, but when this is 0, these two will not be 0. That is not possible. Okay. They are going to be different. So if this is 0, then we say that it is dispersion without deviation. dispersion without average deviation when delta y becomes 0. Okay. Now if this is not 0 but these two are same, deviation in rate becomes equal to deviation in y length. I can make arrangement, I can make some changes here. So for a given set of values, I can have these two becoming equal. These two becoming equal. In that case, I will have no dispersion. There will be deviation, but no dispersion. Deviation, but no dispersion. That becomes deviation without dispersion. Deviation without dispersion. Okay, and this is known as dispersion without deviation. No deviation, that means deviation in yellow color is 0. Okay, that means deviation produced by the first prism is equal to deviation produced by the second prism. Okay, so 1.7 minus 1 times this is 4 degree. 4 degree is equal to 1.5 minus 1 times A. Okay, so this is a 2.8 is 0.5 A. What is A? This will be 5.6 degree. Okay, so I have two. Okay, so I can have this arrangement. I can produce two types of result. Two types of result by adjusting these values. Okay, what are those two types? Those two types are dispersion without deviation. Okay. It is actually mean deviation, but we generally call it as simply deviation. Or I can have deviation without dispersion. Okay, so when I have a combination of prism which produces this result, then it is known as straight, it is known as direct vision combination. Direct vision combination. And if I have this combination, it is adjusted by choosing different values of angles and refractive indices such that I have deviation but no dispersion. Deviation but no dispersion. Then it is known as achromatic combination. Okay. To understand this, and it is this achromatic combination which is very important for us, especially the achromatic combination of lenses. Okay, lenses. We are going back to lenses now. We have already studied lenses, but this achromatic combination becomes very, very important in case of lenses. Okay, let's look at the behavior of a lens when white light is passed. Okay, I have this lens here. Okay, it is also made of some material. Let's say that I have this object O. Okay, now this whole setup kept in monochromatic light. Okay, not monochromatic light. Okay, whole setup kept in white light. Let's say in white light. Okay. Now, how the image forms? From this object, light rays will start. The moment they enter, now different light will bend differently. Okay, 1 over focal length is equal to mu minus 1 over R1 minus 1 over R2. Now, this whole thing is constant. This is geometrical constant for a given lens. But this lens is going to have different refractive index for different colors. Okay, try to understand this. Try to understand the significance. This lens is going to have this same value. This is a geometrical property. It will be same for every color. Every color. Okay, but mu value will be different. Okay. Now with mu, focal length changes. Okay, if mu increases, then focal length decreases. Does that make sense? If mu increases, focal length decreases. If mu decreases, then focal length increases. Okay. What is relation between? Okay, keep this thing aside here. Between wavelength of red is more than wavelength of violet. Mu of red will be less than mu of violet. Mu decreases, focal length increases. Okay, that means focal length of red will be more than focal length of violet. That means the moment this white light, this is a white light, now it breaks into 7 components, and all the components will focus at different points. Focal length of lens is going to be different for different colors. Okay, it will be highest for red and lowest for violet. Okay, they are going to focus like this. Okay, this will be violet and this will be red, and in between I will have all the colors. What it is? Okay, of course there is not much separation because the difference is very, very small, very small. Difference is very small, but still there is difference. The colors are going to be focused at different points. Okay, so I am getting 7 images. Okay, so this is a colorless object. This has no color, white color, but here the image will be colorful. This is a colorful image. Okay, I am getting seven different colored images almost at the same place. There will be very small difference here. Okay, that appears very interesting thing to have happened, a beautiful thing. But this actually is a defect. This actually is a defect. It is known as chromatic defect. Chromatic defect. Okay, what is the remedy? What is the remedy? This is a chromatic defect. I do not want this. Okay. So you see, look at the implications. Suppose that you are using spectacles. You are having some problem in your eyes, and doctor has prescribed you spectacles. So in your spectacles, you are probably using a concave or convex lens. Okay, the same thing happens in concave lens also. In concave lens also. Let's see. This is my white color. This is my object here. And this is how the colors are going to be like separated here at different points. That's how I am going to get my image. Okay, this will be violet and this will be red here. Okay, no, this is violet. Violet is here. Violet and this is red. Okay, you see, there's focal length of red is going to be more than this. Okay, so it is this magnitude wise. Okay, so this is fine. So and all the colors in between here. So suppose that you are doctor has prescribed you some glasses, some spectacles to correct your vision. And if you are looking at some, if you are reading your book, or you are looking at this lecture right now, so you are going to see everything colorful. I am writing with white chalk. Everything will appear colorful to you. That becomes very irritating. It's annoying. That's why it actually is a defect. It is known as chromatic defect. Okay, then how to remove this? How to remove this? Okay. Remedy. What is the remedy for this? what is the remedy? Chromatic aberration. Chromatic aberration or chromatic defect. Okay, both are same. Chromatic defect or chromatic aberration. Okay, now what is the remedy of this? The remedy of this is we use a combination of convex and concave lens to get an achromatic combination. Okay. How? Because these two have opposing behavior. Look at the sequence. This is violet, red here. The sequence is reversed here. Now I have red and violet. Okay. So if I combine these two, this defect, this anomaly will be reduced, and under certain condition, okay, it is totally corrected. Okay. So what we do is we use this a combination of a convex lens and a concave lens. Okay. Let's say that this focal length is f1 and its dispersive power is omega 1. Dispersive power. This is also dispersion. So this lens is made of some material having dispersive power omega 1 and its focal length is f1. Okay. Now this lens has focal length f2 and this is omega 2. Under one condition, this combination behaves achromatically. It becomes an achromatic combination. Okay. What is the condition? Condition for achromatic combination. Okay. Something that you have to remember, it is like this. Omega 1 over f1 plus omega 2 over f2 is going to be 0. If this condition is satisfied for this combination, then this combination becomes an achromatic combination. Now there will be no defect. So if I have this white light, okay, if I have this object here, then all of the image I am going to get at one place. Okay. This is trying to split, this also is trying to split, but then they are balancing each other. But that perfect balance will happen only under this condition. Okay. And problems are asked based on this condition. Now from here it is very clear. Omega is dispersive power. It is a positive constant. This is positive. This is positive. And they add up to 0. That means F1 and F2 must have opposite sign. I can get achromatic combination only by using one convex and one concave. I cannot get achromatic combination by using two convex or two concave. This is a strict condition. One convex, one concave. Okay. The glass that you are using, even though its power is negative, it is a concave lens overall, but then also it is a combination of these two. Apparently you cannot make out whether it is a combination of these two, but it has been made that way. All the glasses, the spectacles that we use, they are actually achromatic combination. They are a combination of these two. Okay. We always make that. Always. Even though it is not apparent from the outside. But that's what is done in all the cases. Otherwise, everything will appear colorful because of dispersion. Okay. Now let's do one problem based on this property. Okay. Let's do one problem. Convex and a concave lens of dispersive powers in ratio 3:5 are used to make an achromatic combination of effective focal length plus 75 centimeter. Okay. So I want to have an achromatic lens of focal length 75 centimeter. Let's say I cannot use a single lens. A single lens is almost never used. We always use combination. Okay. So if I want to have a convex lens of focal length 75 centimeter, then I am going to use these two lenses. I will choose these values. Such that it becomes achromatic plus its effective focal length should be this. Okay. Then how should I choose it? Then what should be the focal length? Find focal length of both lenses. Okay, so I want to make this combination, achromatic combination. Okay, this is omega 1, this is omega 2. Okay, omega 1 over omega 2 is given 3/5. It is given. This is f1 and this is f2. F1, F2 I want to find out. Okay, f1 I do not know, f2 I do not know. Okay? But what I know this 1 over f1 plus 1 over f2, it is going to be equal to 1 over 75. The effective the combination should have focal length of this. So this is given. I want to find this f1 and f2. Can you do that? Let's see. Okay, it should not be difficult to solve. Try that. It's like this: omega 1 over f1 plus omega 2 over f2 is 0. Okay, so omega 1 over f1 is minus of omega 2 over f2. Now f1 over f2 is minus of omega 1 over omega 2. What do you think? Is this right? Okay, so omega 1 over f1, omega 2 over, okay, that's fine. This is going to be equal to minus of 3 over 5. Okay, so I can write f1 is minus of 3 over 5 f2. Now 1 over f1 plus 1 over f2 is equal to 1 over 75. Okay, now this becomes minus of 5 over 3 f2 plus 1 over f2 is 1 over 75. Okay, that's how we do it. So minus of 2 over 3 f2 is 1 over 75. I have f2 is minus 50 centimeter. So this is minus 50 centimeter. This is 50 centimeter concave lens. So what will be f1? Okay, f1 minus 3 over 5 into minus 50. This is plus 30 centimeter. Okay, so if I use a convex lens of focal length 30 centimeter and a concave lens of focal length 50 centimeter, then I am going to get a lens of effective focal length this 75 centimeter plus it will be achromatic. So if I use this object, if I use this lens in my spectacle, my vision will be normal. I will not see colorful things. Okay, this is known as achromatic defect. Now there is one other defect. There is one other defect in lenses. Okay, let's discuss that also. Okay, that is known as spherical aberration. That is known as spherical aberration. It's like this. Now, chromatic aberration. Because of dispersion, a white light, 7 colors, each color different refractive index, different focal length, they focus at different points. Okay, fine. What if I use a monochromatic light? Monochromatic light. Then also we have problem. Monochromatic light. The problem is like this. Whatever we have studied till now in mirrors or lenses, everything was in relation with paraxial rays. Paraxial rays, not the marginal rays. Now, paraxial rays and marginal rays, they have different focal length. They focus at different points. They focus at different points. Okay, paraxial. These are the paraxial rays. Paraxial rays, and these are the marginal rays. Marginal rays. Okay. They will focus differently. They will focus differently. They are going to focus something like this. Okay. So light rays from different part of lens, they focus at different places. Okay. I have this point object here. Point object here. What do I expect? I expect a point image. I expect a point image. Okay. But if I keep a screen here, I am not going to get a sharp point image. What I am going to get is a disc-like image here. It is because different light rays passing through different part of this lens are focusing differently. That's why this is happening. It is known as spherical aberration. What is the remedy? What is remedy? Okay, stop either paraxial or marginal rays. Okay, that means in other words, you allow either paraxial or marginal. Then this defect will be reduced. Okay, that means if I blacken this, if I blacken this thing, if I cover it, I allow my light to enter only through this region. Okay, so the light, so in that case, my defect will be minimized. Then I will get only one image here. So this is the remedy. You will stop either the paraxial or marginal. Okay, so I will cover this. I will paint it black. And that's why you must have seen in many optical instruments. If you look at the microscope that we generally use in our laboratories, okay, we have a very small aperture, very small hole through which we look. Okay, so we stop almost all of the marginal rays. We allow only the paraxial rays through a very small region. Okay, that is done to remedy this defect, spherical aberration. But now then there is a side effect. What is the side effect? What is the side effect? Intensity of image reduces. Okay, so now I am allowing less light, so this brightness will decrease. Intensity or brightness of the image will reduce, it will decrease. Because I do not allow all the light here. Brightness is going to decrease. Okay. Okay, so that's almost it about dispersion. Okay. We covered various topics. It's a small chapter, but many small topics. The chapter is full of many small concepts here. We discussed many things. Okay. Let's discuss one last thing, and then we will conclude the lecture as well as this chapter also. And that's something is very special, very important, and very beautiful natural phenomena that is known as rainbows. Okay. Let's discuss briefly. Okay. Rainbow has its own science. Okay. People actually research the rainbows. They spend their lifetime researching and chasing rainbows. It has its own rules, okay, own science behind, beautiful science, beautiful physics behind it. You will find a whole book written on rainbows. Okay. But here we are not concerned with that detail. Okay, just the basic process, only the basic process. It's very simple, and that's what we are going to discuss. Okay. Before we discuss rainbow, few important points. Let me write down in the beginning itself. Okay, rainbow. First of all, is formed due to reflection. Okay, refraction, reflection, okay, that is total internal reflection. Okay, how they are formed, summarizing it, then we are going to understand how it happens. Is formed due to refraction, reflection, total internal, that is internal reflection, total internal reflection, and dispersion. All the optical phenomena that we have studied till now, all of them merge together and they create a rainbow. Okay, so refraction, reflection, and dispersion of sunlight from raindrops, water droplets, or the raindrops, let's say. Raindrops. Okay? Now, okay, to see this, to see rainbow, okay, the sun must be behind the observer. Okay, that means if this is sun here, okay, then I must be looking towards this side. This is my back, and this is my front. Okay, so the sun should be behind me. Sun should be behind me. Okay, then I will see rainbows here. Okay, red and white. Sun should be behind me. That means in the morning time. Understand this? If you are watching a rainbow in the morning time, that means you are looking towards west. In the evening time, if there is a chance of seeing the rainbow, it is in the west, in the east direction. In the east direction. Okay? Now, third, two types, primary and secondary. Primary and secondary. In primary rainbow, there is one total internal reflection. This process, refraction, reflection, and dispersion, it happens, they create rainbow. In both type of rainbow, primary and secondary, there is going to be all the three processes. Okay. In primary, total internal reflection happens one time only, and in secondary, It happens 2 times. 2 total internal reflection. 2 times. Okay. Now, understood? Let's note down. Sometimes directly problems are asked. Because from this, in primary rainbow, how many total internal reflections? In secondary rainbow, how many reflections? Okay, rainbow is created due to which process? Okay, so all 3 processes. Okay, what should be where the observer should be located to see the rainbow? Okay, so the sun should be behind the observer. Okay, so if the sun is behind me, I'm looking here, I can see the rainbow. In the morning time, you can see it in the west direction. Evening time, east direction. Okay. Now, how it is made? Note it down. How it is created. Okay. How it is created. Let's say it has just rained. It has just rained, and atmosphere is full of raindrops, even though they are not visible. Okay. Imagine this situation. Rainy season. It's a rainy season. It has just rained, and atmosphere is full of small water droplets, large number of billions, trillions, zillions. Okay, innumerable water droplets all floating around in the atmosphere. Okay, let's consider just one droplet. Just one droplet. Okay, this is one droplet here. Okay, making a big picture, otherwise it's very small, minuscule size. One droplet. Here is my sun. Here is my sun. From the sun, light rays are hitting this raindrop. Okay, some light will hit here, some light will hit here, some hit here, like this. Okay, you understand this? Okay. Now let's understand this in 2 parts. Okay. Let's consider a light ray which hits the upper part, and then we will consider the light ray which hits the lower part. Okay. Consider this. Okay. A light ray hitting here, like this, on the upper portion of this water drop. Okay. Now, the moment it hits this water drop, this is a water drop. Water drop. Okay. It is going to enter the water drop. This is my original path. Okay. It is going to break, split. There is dispersion. Do you see this? Now compare 2 light drops, two light rays. Okay. One light ray which is hitting this along this diameter, it goes undeviated, does not deviate. Okay. Now if I take any other light drop here, this is my center, this will be normal. It will be normal here. Okay. This is my light ray. Okay. I just want to find out what will be this angle. Okay. This is a normal, this is angle of incidence, this is going to be angle of refraction. Okay. This is radius, this also is radius. If this is R, this also is R. Angle in air is I, angle in water is R. Angle in water R, air I. Water R, air will be I. Okay. Light goes out like this. This is also I. Okay. Now, if I take this light here, okay, what is happening to the angle of incidence? Angle of incidence increases. So angle of refraction will also increase. angle of refraction will also increase. Okay, it will be something like this here, not here, but maybe here. Okay, this angle will also increase. Do you see this? Are you able to understand? It should not be difficult. As I move above, okay, this angle is increasing, angle of incidence. So angle of refraction will also increase. At this point, all the light rays hitting here on the other surface have different angles. Different angles. They are making different angles. They are making different angles of incidence. And the light is going from denser to rarer medium on this side here. The light is going from denser to rarer medium at this surface. And different light, infinite light ray is hitting this water drop. Out of those infinite light rays, there will be large number of light rays for which this angle will be more than critical angle. Think about this. Infinite light rays are hitting this water drop, no matter how small it is. Okay? They enter this water drop. The moment they enter, they split. I am looking at just one light ray. Let's say it is monochromatic, any one color. Okay? The light ray enters here. At this point, now it is trying to go out. Again, there is change in medium. It is making this is my angle of incidence. Angle of incidence. Okay? The light is going from denser to rarer medium. There is a chance of total internal reflection. For many angles, for many light rays, this angle of incidence is going to be more than critical angle. Then they will not go out. They will not go to the other side. They are going to be reflected. They are going to be reflected. And it is those reflected light rays which create rainbow. Okay? So they are going to be reflected like this. Okay? They are going to be reflected. Okay? This is my red color, this is violet color. Okay? And here, again, you see, again, this process keeps on happening. At this point also, there will be many light rays for which this angle will be more than critical angle. Okay, it will depend on this position here, the position of this light ray, which one is considered. Okay, so for many light rays, this angle is going to be more than critical. Okay, so many of them will be reflected inside, but at the same time, many will come out also. Okay, many are going to come out also. Okay, so it's like they are going to come out like this. Okay, and if an observer is here, here is my sun. This is sun, water drop, observer is here in between. Now I will be able to see the rainbow. This is what, so every drop, millions, billions of drops are creating this phenomena, and all of them mixed together, they create beautiful rainbow. This is known as primary rainbow. Primary rainbow. Okay, this is a total internal reflection, number one, only one time. Okay, only one time here. This is my total internal reflection. Okay. Here also it may happen, but then I will not be able to see. I will be able to see only if it comes out. Okay, this is there is only one here. It is primary. Now what will be sequence of color? What type of rainbow I am going to see? What will be sequence of color? Okay, the sequence of color will be the normal sequence. The normal sequence that we find in Prism, with the same sequence. It will be red here and violet here. Red and violet. The same sequence that we find in Prism. That sequence I see in primary rainbow. Okay, this is red, this is violet. Okay, the sequence that I see from a prism, the same sequence I see in primary rainbow. Okay, you understand this? Now, what is secondary then? Then we are, let's look at some light rays which are entering here. You see, here also, if I am here, if I am flying like a Superman above the sky, above the water drops, then I will be able to see these two light rays. Then that becomes secondary for me. But then, unfortunately, I cannot do that. I am here on ground. So I will have to wait for some other light rays, okay, to undergo two reflections and then reach me. That I don't really have to wait too much. It actually happens, okay. Both happen together. Let's consider the other light rays which are hitting the lower portion of this water drop, okay, the lower portion. Okay, it is this lower portion here, okay. Now the moment they enter, it splits. It splits. It undergoes the internal reflection, okay. It undergoes internal reflection. This is a PIR1. Again they undergo reflection, okay. First time, then they undergo reflection second time, okay, and then they come out finally, okay. And if I happen to be here, sun is behind me, okay. So the rainbow corresponding to these light rays which have undergone total internal reflection 2 times, then the rainbow created because of that process is known as secondary rainbow. Secondary rainbow. And in this rainbow, the sequence of colors is reversed. Okay. Now I have violet here and I have red and violet. Okay. This is about a very brief general discussion about rainbows. Theoretical questions are asked, okay, numerical problems will not be asked. You don't have to worry about it. So that's it. Let's conclude this lecture and this chapter also.